Hello guys, so in this video we're going to be sketching the galvanic cell for the following two half reactions. So the first one we have is going to be Fe2 plus going from aqueous to Fe solid and F2 fluorine gas going to fluorine ions. So we have the E naught red values for both. Now we have to convert one of them to oxidation, and in this case, it's going to be uh, iron. So when we flip the equation, we got first of all F2 fluorine gas plus 2E minus gives us 2F plus aqueous. E naught red is going to be plus 2.87 V. On the other hand, when we flip the reaction for iron, we also flip the sign of E naught red and it turns into E naught ox. Is 0.44 volts. So now to calculate E naught cell, we add the two values and we get 3.3 positive 3.31 volts. So we require for E naught cell to be positive. So now when we have these two options, now we're going to draw out and form the shorthand for this equation. So there are two sides to this. There's an oxidation side and there's a reduction side. So on the oxidation side, iron solid is going to go to iron 2 plus aqueous ion. On this side, as fluorine is a gas at standard conditions, we're going to need an inert cathode. So that one is going to be uh, platinum in this case. We use platinum. And we are going to get F fluorine to gas plus, not plus, and the 2F minus aqueous of standard molarity, which is 1 in the solution. So it's going to be standard molarity over here as well. So as we have our shorthand and we have our E naught cell, we are going to sketch out the cell itself. So we have two beakers, this side. This is going to be for oxidation. This is going to be for reduction. So we have our fluids here. We got our anode and we got our cathode. So these are connected with a voltmeter in the middle. So the reading on this voltmeter is going to be 3.31 volts. So this over here is going to be Fe solid. This one's going to be platinum solid. And yes, so we're also going to need a salt bridge. Redraw that again. So the salt bridge is going to be NaCl, but in this case, we will write it as Na plus and Cl minus. So in the oxidation beaker, we are going to be forming Fe2 plus ions. And in the reduction beaker, we are going to be forming sorry, F minus ions. So We have the salt bridge in the middle. So the salt bridge has three uh, uses. First of all, it connects the circuit and allows for electrons to flow. Secondly, it maintains electroneutrality. And finally, it prevents overvoltage. So what do the all these mean? So for the first one, it connects the circuit. So if there wasn't a salt bridge, the electrons won't flow, so it won't matter. For option two, electron neutrality. So electron neutrality and overvoltage, what that means is as the cell is being used or it's working, more and more Fe2 plus ions and more Fe minus ions are formed in both beakers. So to prevent this from happening and running the cell smoothly, uh, Cl ions from the salt bridge will cross over into the Fe2 plus solution uh, to provide some neutrality, and the Na plus will go into the F minus aqueous solution. So just write these here. This is so everything is in order, nothing is being there's no over voltage, and everything is running smoothly. The electrons, they flow from the cathode to the anode. So that is basically what a galvanic cell is for the most part. So that is the sketching of the galvanic cell. Now we have to find out a couple values. First one is going to be, we have already found E naught cell, which is going to be 3.31 volts. Next, we have to find delta G, that is equals to negative moles Faraday's constant and E naught cell. So in this situation, there are two electrons on each side, so the moles of electrons is going to be 2. So we have negative 2. Faraday's constant is 96,485 uh, coulombs per mole. This is mole. And the E naught cell is going to be 3.31 volts. So moles cancel out. And in the end, we have only joules are left. So the value we get is going to be, let me calculate, is going to be negative 638,730.7 joules, or si one, yeah, or negative 639 kilojoule. So this makes sense. Our delta G should be negative, and if our delta G is negative, it means that this is a spontaneous cell, spontaneous reaction. And as we know, galvanic cells are spontaneous reactions, so it does back up our findings from this whole sketch and our cell values. The second thing, or the last thing we have to find out for this question is going to be constant K, or equilibrium constant. So delta G can also be used in the form of negative uh, gas constant, temperature ln of K. So in this situation, we already found out, so it's going to be negative 639 kilojoules for delta G. negative. This is gas constant. It is supposed to be 8.314 joules, but as this is in kilojoules, we have to have it as 0.00, yeah, 0.008314 kilojoule per mole. And then we multiply. So these are standard conditions. So standard condition temperature is going to be 298 Kelvin and multiplied by ln of natural log of K. So when solving this out, we're gonna get the value of this is gonna be 2.47757 or negative 2.477. This goes around here, divides. So ln of K is equals to uh 257.9, and then we take the put it to power, take it with the exponential power, 257.9, and the value we get for K, this is going to cancel out, is going to be around 1.6 extended power of 111. Yes. So that is our constant K. And in this case, K should be uh, bigger than 1 for it to be spontaneous. And in this case, K is a very huge number. That means it's highly spontaneous. So just as a recap, we found E naught cell. We got the two half reactions. We drawed out or written out the, let me highlight this, the shorthand right here. So we use platinum for our cathode because fluorine is a gas at standard temperature, at standard conditions. So we need an inert cathode. This is our um, sketch for our galvanic cell. We found out the value of delta G and we found out the value of delta K. And that'll be all. Thank you very much.